Do you need to? Can you guys hear me? Yes. We talked a lot about verification yesterday. So we're not going to try and spend as much time just talking about the architectural verification part, but more how DV has evolved, where it is right now, and at least from a tensor standpoint, where we see it going. So with me, we've got Mansoor and Radha. Um, I think we represent a fraction of the expertise in the team. And let me go to the next slide. We'll come back to this. And between this team, we have worked on all of these architectures. So one cool thing about RISC-V is it's new, but at the same time also lets us take away a bunch of learnings from all these different instruction set architectures and deploy it back into RISC-V. Uh, oops. Try to go back. Yeah, it's not going back. One sec. Finally, all right. So we'll break this into three sections. We'll talk a little bit about just DV evolution, like I was saying. And then Mansoor is going to step in and talk about just how we envision a scalable test bench environment. And then Radha is going to talk about a real case study here, how we bring up a high performance design from scratch. So this is how, when you're trying to build a traditional CPU from scratch, this is how it typically works, right? You first start with architectural tools, and when I say architectural tools, it's instruction set simulator, it's stimulus generators, it's test cases, it's coverage models. There's a bunch of things that go in architectural tools. So you spend a bunch of time in there, and the numbers here kind of represent what percentage of a design cycle goes into those activities. So almost a fifth, and this is just my experience working on multiple from scratch designs, is this is roughly the breakdown. Right, a fifth of the time that you spend ends up going into building architectural tools, building them, maintaining them, supporting them, um, and so on. So you start with an architectural tool, then you go into do some sort of test planning. And while I'm talking about CPUs, this generally applies to a lot of just verification work, right? Whether you're working on routers, whether you're working on PCIe, USB, but you start with tools, you switch on to test planning, and you spend a boatload of time. All right, where's my spec? How do I write some sort of stimulus for it? What are my different cover points? How do I think about it? Uh, and then you move into, okay, now I have to do coverage closure. You start coverage development, you work through it, you spend hours, months. In some cases, I've seen many, many months of a processor design cycle spent on coverage. And then you say, okay, I feel good about what I have thought of. Coverage is an intent, is what you can think of, whether it's being covered. And then finally, you go into everything that I could think of, I've covered. Now, let me just go find bugs beyond what I haven't thought of. And eventually sign off, right? What are my bugs coming? Am I getting through ECOs for an actual silicon? And so progressively, you spend less and less time. And the biggest challenge I've seen over the years, that you spend so much time in your initial development that you kind of lost track of the forest among the trees. And and this is how traditionally CPU teams operate. And across this team, we worked on CPUs from AMD, Apple, Intel, um, Microsoft, Amazon. I'm probably forgetting another 3 or 4 CPU companies here, but and this is really every single place. This is really the mindset. This is how it works. So what happens is you start with that initial investment. You spent a ton of time building these tools. You hire a lot of people. We've seen teams, verification teams up to 200, 300 people. Uh, and then you spend a lot of time communicating between those people. All right, who's writing that test? Who's working on this small subset of an instruction? I filed a bug, throw it over the wall. Somebody is going to debug it. Third person is going to fix it, and it's rinse repeat. And then the biggest problem I've seen is when you're building a high performance CPU from scratch, you start off and your decisions on methodology are entirely driven by your first generation. And how many times have people worked on a second or third generation design and we have said, oh, well, we have to add this patch on top of the hack that we did so that we can support the third generation because we decided on methodology 4 years ago. So we just incur a lot of technical debt. Um, this is just kind of my rule of thumb. Every generation you work on a given design, you spend a third more time supporting what was legacy. And so what happens is by the time you get to the fourth generation, your design cycles are now 2x of what you've done. This is very counterintuitive. You would think that every time you're working on a derivative, you'll end up spending less time. But in reality, and we got a really good lead in with Jim, Raja, Naveed, and Professor Mateo talking about how important verification is. This is really what happens. I've seen cases where to add one configuration bit in the design, single configuration bit, what happens is I got to go change my instruction set simulator. I have to go modify these 500 directed tests. I have to go change these 3 random code generators. Then I have to go change these 5 test bench environments. And so to change one bit, you end up saying, I'll need about 2 months of work. Right? It boggles your mind. And this is why you say verification takes so much time, is because we think of it in that fashion. So I'm going to pivot a little bit and just stay on that same theme, right? x86 and ARM are legacy. And when I say legacy, I don't mean that they're not going to have innovation, but they have a lot of just legacy technical debt. And here's a really good example. So anybody who's worked on CPUs, if you look at like a boot sequence, on an x86 core, it's thousands of instructions. You start, you go into real mode, right? And then you go somewhere to do a jump. And then from that jump, you go enable something. You enable paging. You do 50 other things. And by the time you get to just basic boot, this is nothing fancy. It's not even getting into microarchitecture. This is software. You spend thousands of instructions. ARM's a little bit better because it kind of split. Okay, if you're doing thumb, then don't do this. If you're doing, embedded, don't do this. If you're doing V7 versus V8, but it's still hundreds of instructions. Do you know how much time, how many instructions we spent on RISC-V for boot? 2. It took 2 instructions to go from, yes, the CPU is up and running. And that is because there is no legacy baggage. And the way the instruction set architecture is defined is you have a base ISA and you have a bunch of instructions that add on top of it. That is technical debt. And I'm sure when 8086 started, it didn't take thousands of instructions, but it's just built on it one by one. What's going to prevent RISC-V from not getting there is really how layered that architecture is, right? x86, I don't have any intention of running any FPU code. I still have to go initialize, a gazillion instructions for my floating point registers, my floating point control word, or status word, right? RISC-V, you don't support F, that's fine. Your code compiles without any F extension, and then you're up and running, off to races. Compatibility tests. I think just between the 3 of us, we worked on x86 and ARM, hundreds of thousands of compatibility tests for each of those ISAs. Right? RISC-V, the way it's developing, at least for us, I see maybe getting to 1,000 tests, right? And the big difference, most of those are manually written, or at least at this point have to be manually supported on x86 and ARM. RISC-V, pretty much everything we have is automatically generated. And it helps because you suddenly have a new instruction, new extension that gets introduced, and you just add, certain configuration. And it's not just us, right? We had talks from Encore yesterday, from Valtrix, and then those companies are doing the same thing. So the innovation part here is get as much away from making it more manual and laborious process, and get more into how much you can generate code and look at the baggage that you'll get rid of. Architecture checking. Once you have less state, because you are a layered architecture, there's very minimal, right? On x86, it's huge. And then cost of adding new ISA features. I think Jim's talked about data format, but it's not just limited to that. If you have to add a new instruction, same process to go change 5 things in the ISA, in the microarchitecture implementation, which will remain the same, and then I have to go change 50 things in the DV collateral. And it just goes on, and it exponentially increases. So I don't think anybody here would disagree that the architectural innovation on legacy ISAs has been linear. There have been stuff that's gotten added, right? You started with basic floating point, added SSC, SSC2, SSC3 on x86. Then you got vectors, ARM added SVE. So there has been innovation, but not at the same pace as the effort to validate that innovation. And, and that's something that RISC-V can fix with more collaboration, right? Not everybody has to do every single thing. Um, yeah, 30 years of baggage. So how many people still have, stuff from 30 years ago that they still use, right? And the way to do this really to move forward. And then one final thing, just on the same theme. If you look at high performance designs from scratch, you can broadly break it into verification for architectural functionality and verification for microarchitecture. So architectural functionality is really the ISA. Microarchitecture is your implementation, how your VTBs are implemented, how, what is the out of orderness of your machine, how much effort are you spending in verifying your out of order loads versus stores versus because the it's a finite space. But the reason it becomes this complicated is the legacy ISRs like x86 and ARM have spent a ton of time trying to make patches and hacks into existing instructions that you have no choice but to spend that much time. Unlike RISC-V, right? Highly modular, start with the base extension, base, and then add extensions to it. So if you're likely silicon bugs are going to show up in your microarchitecture, why would you spend most of your time doing architectural verification, right? So it needs to evolve. If we keep going this way, this doesn't scale. Right? You cannot do it with large teams, and you cannot do it with architecture verification as your primary way of doing things. So what we try to do, Ascalon's high performance design, Shrikant talked about that yesterday, is spend more time thinking about it from a software perspective, right? How do you do code generation, right? So in our case, a lot of our verification infrastructure is generated. We use open source tools for reference models. We use open source tools for instruction generators. We even use open source tools for our build infrastructure. And we did a presentation a couple of weeks ago, a couple of months ago in DVCon about it. Because that's how you scale. The more manual work you do on this, the more maintenance, and eventually by the third or fourth generation, you're spending 2x the time, right? Like I was talking about. So RISC-V provides that really interesting reset point for how we think about DV. Right? If you think about clean extensions, you're verifying individually in isolation. If you think about clean interfaces and how those extensions are mapped to those clean interfaces, then you can start thinking about configurability. So there are 2 or 3 open source instruction set simulators on RISC-V that I am aware of. You've got Whisper, you've got Spike, you've got Sail. All of them are based on configuration files. You support these 4 extensions, give that as an input, and then the ISS works accordingly, right? If you pick any of the proprietary reference models from any of the large companies, they have built 30 years of technical debt. And in order to make one change, it'll take 6 months to add a feature. And that's really not the right way to go. So you need to have your architectural verification environment be much more flexible. You need it to be flexible so you can take in multiple stimuli generators. We had 3 companies, 3 stars, and collaborate with other RISC-V companies, the better it is going to be for our implementation, right? Rather than spending all that time trying to do everything by ourselves. But what that requires is for the environment itself to be very scalable. So we can run multiple reference models, we can run multiple stimuli generators, and then we can deploy a combination of open source and commercial solutions, all working together. This just, having worked through multiple large companies, this doesn't typically happen, right? Because the mindset is always to go with a proprietary solution. And then focus more on the bugs that you're going to find. So the other thing that we're trying to do is try and use a lot of our infrastructure and try and use generative AI. So I'll probably get into that a little bit later. Just skip ahead. So I'm a big Star Wars fan. Right? RISC-V is the rebellion. You have to have, go down the path of making sure that you're doing things in a new way. Right? You build reference models, they have to be modular by design. Right? You do not want to carry the technical debt of your legacy stimulus. Custom instructions, there is a very well-defined custom address space, opcode map in the opcode map where you can just go and add your custom instructions, right? Um, Certainly, there are the way RISC-V International operates. There are committees which decide new extensions coming up, but there's a lot of freedom for any company to go innovate on instructions. You work on an accelerator, you work on something which is speeding up FFT, go write your instruction and implement it, right? Because at that point you have to manage your own software stack. This helps. It's a huge help. It reduces the cost of getting stuck with a decision made on the first generation design, rather than having to go and make multiple hacks to it later, right? And then a really cool thing about this, the ISL lends itself so cleanly to formal, right? So that you're not spending your time doing as much work on stimulus development, and you're able to leverage a lot of exhaustive testing without spending the amount of time and people and just complexity on it. It's incredibly challenging to formal on x86 and ARM, and I've tried that both, right? But RISC-V, just by nature of how it's evolving, makes that so much easier. And then that in a modular reference model, in a modular stimulus generator, right? In a modular methodology of creating, writing, and maintaining test cases. But then we want to spend a lot of our time on micro-architectural verification, right? We talked about architectural verification yesterday. And so some sort of guiding principles, you should be finding most of the bugs at the lowest level of abstraction, right? You should have block level test benches. If not block, even lower than that. If you are trying to verify a floating point unit, just create a wrapper around floating point unit. There's no point in finding those issues at the SOC level. That's just a disaster, right? If you have to get down that path. You need to work on test bench components. A lot of this stuff that we're building, we're going to try and open source. You need to leverage test bench components that can be used across multiple blocks. Right? If you have a BFM for one block, it can be used as a driver for another block, right? And that is how the whole mindset has to change a little bit for CPU verification. You cannot keep doing proprietary solutions for every single thing. We started using beta testing GitHub Copilot a couple of years ago. And there are two things that came out of it. It wasn't ready for doing everything, but it was terrific for code assist. So for people who are familiar with paging modes, now one of our engineers, he wrote code for supporting a paging mode in a stimulus generator, and then you let Copilot scan, the codex model scan your code, and it essentially generated the same code for the remaining two paging modes. Right? It not just generated the code, it let you mimic the coding style, the function naming convention, whether you're using camel case or just uppercase. So, and this was 2 years ago. Models have dramatically evolved from that point. How do you use beyond that? How do you go beyond that? Is you start with standardizing things. Standardize your log files, standardize your interfaces between blocks, and you gather information from those, because at some point you'll have enough data, or you can use a pre-trained model that you can infer information out of it. You can make your debug faster. You can run, more adaptive, smarter test cases that you can do. We already do a lot of this, by the way. For example, um, we, for our open source workloads, one thing that we're trying, and this is pretty cool, right? Anybody can go, and this is ChatGPT. Just go to ChatGPT, put a link for a GitHub repo, which is just pick a particular workload, right? There are a bunch of libraries which are single-threaded. And then, and this is prompt engineering, apparently that's a word now. So it's prompt, you type in there, I want to do this, but I want to marry it with OpenMP or pthreads. What it would take is take your single-thread workload, and it's going to create synchronization routines, and it will create multi-thread workload out of something that already exists. Right? This activity, and I've done this in the past, it was 1 year worth of effort. Time to get the right sequences right, and you're able to get that. Right? It takes, 30 minutes to do something like that. Sure, you have to massage it, it takes over time, make sure you've got right libraries and everything. But this is a big, big help. And so, especially for DV, I think this is where small companies and startups will jump on this much faster than a bigger company. Is there are ways to take what's out there and tweak it for your purpose and make it more productive. So one last thing. So this is just an example of one of my colleagues works on code generation for our test benches. Is again less manual work. I'm sure there are a bunch of DV engineers in the room, or wannabe. You take a spec, and you, based on that spec, write a design. Um, write a monitor, write a driver, write a checker, and then what happens is the spec changes 2 months down the line. You have to go back and change your interfaces again, change your drivers, change your checkers. Um, but instead, what we're trying to do is take the design, and from that design, abstract out what are the interesting signals, and then create a mapping of those signals. Use that information to go automatically generate system verilog monitors, system verilog drivers. You still need to spend time in understanding spec and writing scoreboards and checkers, but you take out all the sort of the grunt effort by maintaining or having to maintain these components. So this is yet another example. The next step on this is hardware or software netlist, right? It's able to understand that and give you interpretation out of it. So you can do that with even RTL signals, and it'll tell you the timing diagram. If you give it some, an interface code, it'll give you timing diagrams. Okay, this is the delay between signal A versus signal B. It's already evolved at that point, and this is not even GPT-4. So this is really the way to go. And this, with combination of RISC-V and just the reset of how you do DV, this is now a time to do it. Cool. Right. I'm going to switch over.
All right. Thanks, Divyang. So I'm Mansoor. I'll talk about the test bench environment. All right. So like Divyang mentioned, the goal at block level verification is to find most of the microarchitectural bugs. So at core level, what we want to do is to find really the cross-unit interaction bugs, the interface, and also just general architectural bugs. And so this is where we are able to run assembly test cases. So the goal that we had when we were designing our test bench was to be scalable, portable across platforms. So in the block diagram, you see a generic RISC-V core complex. So we could substitute any RISC-V core design over there, and it would talk to the test bench through some kind of bus, right? So we would have, in our design, we have a chai, and then we have an XI transactor, so we have a bridge in between. But the architecture, the protocol could change, and we could just substitute in the bridge to talk to the same test bench. Right, and some design decisions that need to be made early on to be compatible with both simulation and emulation. So we decided to use only synthesizable system Verilog and C++ in our test bench environment. Different vendors, even across emulation platforms, right? With vendor A versus vendor B versus FireSim, which is an open source solution, or similarly in simulation with across different vendors, or using Verilator as an open source simulator. We we decided to write our own models and transactors, right? So the transactor talks to the system model in our test bench, which kind of routes the incoming traffic to one of the appropriate devices. So whether the traffic is meant for your memory DRAM model, we have our HTIF, which is a stand-in for our I/O peripherals, and or interrupt controller, essentially. Yeah, and also the same test bench and so on. So another important thing was to be flexible to make the same test bench environment work with different duties. So when we started, our design was not mature enough to be able to build our or test our environment. So we started with an open source RISC-V CPU core. We have the Boom from Berkeley, and we also have the CVSX from Open Hardware Group. So we could use these cores and plug in with our test bench environment with a standardized kind of interfaces and build our environment, and then kind of just drop in, substitute our own Ascalon design instead of the Boom or CVSX. So that kind of gives you a way to accelerate your, and gives you a lot of flexibility. Of course, which means there would be some custom configuration that needs to be done for your specific CPU. So we have mechanisms to configure that. We have an architectural configuration done through Whisper, so which is the instruction set simulator we're using. So a Whisper JSON. We have microarchitectural configuration also configurable through YAML. So you could have things like number of retires per cycle, your physical address width. All of these could be parameters you can change when you're substituting a different design. Right, so and there's also system configuration. What does your memory map look like? What are the different memory regions? Things like that. So all of them go in as separate configuration files into your test bench. Okay, so briefly talking about Whisper, the open source instruction set simulator. So this is done by Joe Rame, who is a colleague, and it supports all the major RISC-V extensions, and it's super fast. It's like we've benchmarked it to be over 150 million instructions per second, probably one of the fastest instruction set simulators out there. And we use it in conventional ways and also some unconventional ways. So the conventional way of just doing core level lockstep checking with co-simulation RTL versus the model. But we also use it in other unconventional ways for things like block level checking, where the model is able to break down the instruction or even at a micro-op interface level granularity, and we can take the micro-ops and do a check at block level unit boundary as well. And we also use it as a disassembler for some of our trace work. Yeah, and we also used it apart from DB. We also use it in architecture modeling, performance modeling, for trace generation, benchmark analysis. So I think Radha will talk about that a little bit in more detail. And this is where you can find all of our open source kind of collateral work, right? It is within the Tenstor and GitHub repo. You can find folders for Whisper, the instruction set simulator, and also the test bench, which is under the COSIM folder. And there are also a bunch of stimulus that we have. We have the vector tests, and we are kind of grouping them all into like a DB kit that you can use to get started. You can put together a test bench within like days, if not hours, which is something I could not think of before. Okay, yeah, with this, I'll just hand it over to Radha, who will talk about bring up.
Cool.
Hi, good afternoon, everyone. So starting something from scratch is never easy, and we were starting a fully functional, out of order, high performance core from scratch, and that path did indeed have quite a lot of challenges. We would like to share some of those with you. So when we start something from scratch, especially both design and verification, both verification components, both were not fully functional. So how did we go about it? So one of the process what we had kept it was, let's keep it very simple. So we started with something as simple as a NOP instruction. We got it through the entire pipe and got it to retire. So we started with something quite simple, and then we started seeing how we can further take it up. Even to take a NOP instruction and fully send it across the pipe, we had to work around quite a lot of things. For example, we had to even force the PC to start at a right location for the fetch unit to start. And also, some of the other aspects, like some of the logic could not have been implemented at all. So we had to either force them or tie it off to get the right things. And the other aspect is we had to preload the caches as well. And as we start scaling up, we had to scale up very consciously as well, because we had started introducing quite a lot of hacks, or I would say quite a lot of constraints. So we had to start, when we moved from NOV to single cache line of instruction to multiple cache lines, and to even thousands of instruction with all the mixed loads and stores, etc. We had to scale up consciously while we are taking back some of the hacks or constraints we had introduced. And so we had scaled up from arithmetic to load store branches and to mix of all possible RV64I instructions. So now we have a bunch of instructions working around. So what's the next step? So we were just thinking from backwards, what could be a good intermediate milestone we could look at? So one of the milestone which we thought was, why don't we boot the Linux? So then when we decided that this could be our intermediate goal, we started breaking down the problem. So what all features would be needed to, uh, to ensure that we can boot the Linux cleanly? So we started analyzing the foundational ISA features, and we saw that the foundational ISA features to boot Linux would be RISC-64 IME, and we needed at least one paging mode to be up, and also the privilege modes, and the exceptions, interrupts, etc.
See, the water one.
And since we are still starting up from scratch, we wanted to break down the features still further. For example, we took the paging mode and we saw what exactly we need to prioritize. So we saw that, okay, 4K and 2M, if we could bring that up cleanly, then we should be good for the Linux boot. So we started breaking down the problems still further and started prioritizing those. So both the design and verification aspects of those foundational ISA features were prioritized ahead of the rest. Okay, so now we have cleaned up the foundational ISA features. How do I boot the Linux? So Linux has around 66 million instructions. If I try to start running it on a simulation, it's going to take a lot of days, almost a month. And if we go about it and then we start onion peeling the issues, okay, we start running it and then we hit some issue, we fix it, and then we again go back and retry it, it's going to take a lot of time. So what did we try to do? We try to keep it simple and we try to do something cool as well. We started parallelizing it. So what we did was we had our ISS, which is Whisper. We took the Linux and then we ran it entirely on Whisper. And then we took snapshots at the desired instructions. So we divided the entire ISS run into smaller instructions count. And then we took an architectural snapshot at each level. So the architectural snapshot would include both the memory and the register sets as well, and the CSRs. We took the snapshot, and then we can replay that directly on the DUT. So that kind of ensure that we can parallelize our effort entirely, and what could have taken us a month, we were able to run parallelly and find issues even in the lost snapshot ahead. So that kind of helped us in fastening up the things. So this probably gives a glimpse of what we had underwent so far. Over to Divyang.
Yeah, thanks. Got it. Thanks, Radha. Yeah, so this is really a good takeaway. Why you want to go find issues which you'll find in silicon. That running a bunch of add instructions and spending days, weeks, months is not the right return on investment. You want to get into starting to running operating system. You want to start running workloads and benchmarks, things that the actual silicon's going to run. Right? And that's going to get you the most bang for the buck. So rather than spending 75% of your time verifying an architecture, try to think of spending that time verifying the microarchitecture, because RISC-V allows you to do that in a very simplistic fashion, right? The way it's built in a modular fashion. So yeah, it's time to reset how you think about processor verification. And I mean, RISC-V gets you that sort of a timeline, that checkpoint to do that. Thanks.
So food is almost ready. We have time for 2 questions. No, don't go anywhere. So we have time for 2 questions. The sooner you ask them, the sooner we eat. So I saw somebody over here. Oh, wow. Here comes the big one.
This for Radha. I didn't hear you say how long it took after you parallelized it. You said it takes a month to do the Linux boot.
On
but
simulation.
yeah, but after you did the speed up,
We were able to complete the parallel process at the max within 10 hours.
10 hours. Okay, thanks.
There's one over here.
So actually, we are writing test bench to verify a design. So there's a framework called SV unit, which verifies the test bench. So are you planning to implement that or to verify the test bench?
So Could you please keep it close? I didn't quite
Oh.
get that.
So there's one open source framework called the SV unit, so which actually verifies the test bench which we write. So you are have you implemented anything like that, or are you planning to implement in future anything like verifying the test bench?
So the test bench flow that I was talking about, we are going to open source it. So and we are looking at anything that exists outside. So we looked at there's something for PySV, and then somebody just reached out, and we're going to start looking at something like EUVM. So there are a lot of open source flows which allow you to generate test benches. And anybody, I strongly recommend spending more time in exploring this and generating them, so that you don't have to do that repeated work.
Okay, we're going to take a break, go enjoy some lunch downstairs, and we will reconvene here at 2 p.m. So we've got about 50 minutes. Thank you so much. Hello, everybody. Let's go ahead and get back on track here. So we are now going to move to an academic portion of this RISC-V event. You all remember Divyang? Divyang presented just a few minutes ago, and he's running away right now. Okay. Divyang's going to host a panel, what we're calling an academic panel of professors and students. So Divyang, here you go.
See if I can get the other mic.
We'll share at this point.
All right. Thank you, Bob. All right. So this hopefully is a lively discussion. I got a preview of it right before. So we've got, Bob, do we have somebody on? Okay, perfect. We have Professor Kripalani on Zoom. Thank you for being with us. And then Professor Madhura and Chester, I'm sorry, with us. And then we've got some representation from the industry and from the students. So the theme here, we're going to follow two different trains. One of them is really talk a little bit about how academia, industry, and students are being prepared for compute. Right? How do we get more into high performance compute? How do we build fundamentals around that? So we'll have, hopefully a lively discussion around that. And then we'll pivot a little bit and talk about just challenges and opportunities on RISC-V and open source, and how different communities, whether it's the educational community, whether it's students, professors, or industry can collaborate and help. So just to get the ball rolling, let me start off a little bit on the Zoom. Professor, can you hear us?
Yes, I can hear you. Can you hear me?
Yes, thank you.
Yes, yeah.
So let's kick it off by talking about a little bit about what are colleges doing right now, especially around building strong fundamentals on computing. We've got a big requirement of engineering talent coming up around need for high performance compute, and this can be CPUs, this can be GPUs, this can be AI. And so what exactly, how exactly are colleges preparing students for that? What are, what they're doing right now, and what more do they need to do? And just sort of your perspective, and if you can kick us off.
Yeah, I can talk about IISc in Institute of Science. So there are, there is, if you talk about computing, we have a program on AI, artificial intelligence. We have a degree, BSc degree course on maths and computing, very specifically for that. And that is not system building, mostly the theoretical background. And then we have the postgraduate and research programs in computer science, system science, microelectronics, electronic system engineering, everywhere, these kind of high performance computing activities go on. And we have a group working on quantum computing, and a lot of people across departments works on various AI, ML, or anything you can talk about. And I can talk about my group, my lab basically builds high performance accelerators, mostly FPGA based in bioinformatics, machine learning, And we also develop course for computer architecture, RISC-V course, and we have developed RISC-V course with, vector instruction set, which accelerates um, ML kind of application. And I have a course which teaches the RISC-V design, basically the processor design, and the focus is on RISC-V. So I'm not very sure. I'm sure in the Indian universities, the AI is being taken up, but I don't know how much of chip design. We always felt that is a bit lacking. And METI has this initiative of SMDP program, which is going on well in many universities in India. Okay, so that is preparing a lot of students for chip design in this field. Yeah, I think I would let others.
Thank you. Please feel free to jump in. From your perspective, professors, how exactly do you think students are getting prepared for compute from your perspective?
Yeah, so very, very similar to IISc. So IIT Madras has also I would call it like two different types of categories. So one is where the applications are present, and there's a lot of interest among students for applications. And these would actually include AI, ML, all the data sciences. On the other hand, of the side of the spectrum, we also have a pretty strong systems group. Um, so especially I'm from the computer science department, so we have faculty doing some cutting edge research in HPCs, computer architecture. So we work with RISC-V quite closely as well. So we've got students, interns, quite a bit of interns who join us during the summer. Many of them stay for more than a summer and do their projects also with us. So one thing which we've actually done to help students, especially from the systems perspective, is try to design our core courses, core undergraduate courses, keeping RISC-V as a platform. So I know of one course in the computer organization in the electrical department, where the objective of the labs and assignments is to essentially come up with a RISC-V processor by the end of the semester. I think probably you must have done that course. And in the CS, we also we have an equivalent CO course, but look at the architectural perspective, look at how interrupts. So we actually have labs to have interrupt routines on RISC-V. And then we go to the 5th semester where we have the operating systems course. Now, this too is also built over RISC-V. So we start, so there was this pretty famous, from a teaching perspective, a pretty famous operating system by MIT. It's called the XV6. So very recently, they've actually shifted from x86 to RISC-V. And yeah, it was a big, a great thing for us because we follow the XV6. We've been following it for quite some time. And like you mentioned in your slides during your talk, right? So anyone who actually goes through the boot up process of an x86 processor, it's a Herculean job. And teaching it is much more difficult because now you have to tell students why is there an enable A20 present, and it sounds more like a history class. So all that is gone, and we've shifted teaching OS, or many of us have actually shifted to teaching RISC-V based operating systems. And yeah, so this essentially leaves a very good platform to continue research, get them ready for industry with these very strong foundations. We have also multiple research programs, master's, PhD, and so on. And quite a few students are actually focused on developing solutions for RISC-V. So for instance, my lab, so we work at security aspects of RISC-V. So we look at enhancing the architecture, for instance, to handle like software-based vulnerabilities, like simple things like memory vulnerabilities could be very efficiently handled in the architecture. Of course, now we look at different trade-offs between performance and security benefits and so on. Yeah, so there's a lot of things which are actually have started, and a lot of it is in the IITs.
IISc, IITs, and so on. And what we would really need to see happening is to also spread this technology to the masses, and where because the requirement for such computing applications, things, and so on is quite large, right? And a few colleges may not be able to support such requirements.
Thanks. I haven't heard 820M for a long time, so that's a blast from the past. And Professor Modra was saying earlier that we're doing a lot more on RISC-V now in PES, so if you can comment.
Right. Yeah, so at PES University being a private university and with a lot of flexibility to revamp courses, where we've been able to introduce RISC-V. I think it's the third run now. So we are talking about revamping the curriculum, computer architecture, advanced computer architecture curriculum, and the number of students that we handle are about 180 plus 350 every batch, right? So we have been able to scale that very well. RISC-V, so students coming out of PES now are well versed with the RISC-V ISA. We've collaborated with Codicip very well. So the way I look at it is curriculum is one part of the story. As a professor, you have to not just look at curriculum, but you have to look at hands-on experience that you can give the students, without which it's a history course, right? So that is what we have been able to do very successfully at PES. So Codicip has been like the professor's best friend. I call Keith Graham from Codicip as, my best friend, because he has been very fantastic in terms of setting up exercises for us, which we can readily use, and we have been using it with the Codicip environment. We have a bunch of exercises that have been facilitated both at the beginner level of computer architecture, advanced computer architecture. We've been given licenses 180 plus that are accessible. Students can access them at home, at their leisure, web-based access. They're able to build RISC-V processors, generate hardware, do cycle accurate simulation, add instructions, understand profiling. I mean, it's amazing, right? So we have been able to do it very successfully. In terms of the curriculum, so this is what I say as the baseline. We want the students to be able to use RISC-V, and this is what I mean. Beyond this, we have been running successfully, we have been running research projects based on RISC-V. We have been funded by the Semiconductor Research Corporation. A few of my students are here because they have this edge of knowing what RISC-V is, how we can build RISC-V. They're able to build larger systems out of RISC-V, right? So I think I'm very excited to say that the students are just waiting for more. I mean, if we can push in, they will just run.
Yeah, that's really interesting. What do you need more from the industry?
Right. So I was, just at the lunch, I was talking about it, right? All of us need to get together and say, okay, we want this big challenge. All of us go towards this big challenge, whatever it is, right? And all of us, irrespective of where we come from, RISC-V doesn't matter if it's industry or academia or anything, right? We have to give ourselves this challenge. I think yesterday the RISC-V generation of RISC-V using ChatGPT is a fantastic place to start. I think we should get together on a monthly meet or a weekly meet, and students are there. I'm telling you that they are waiting to grab onto the challenge that we give them, right?
That's really interesting. Well, what do students think?
So, from a student's perspective, we are just open to face any challenge and come up with innovative solutions once the support is there. So we just want to bridge the gap between the academia and the industry. So when industries come to academia and collaborate and come up with new programs and new courses which are mostly aligned to industry, then we even get more industry experience right when we are at the college.
So talk about that a little bit more. What differences do you see right now you study something and you go work at a company on RISC-V. Can just enumerate for us some tangible differences that you see?
Yeah, so when mostly like the bridge is like sort of blurring, the line is blurring now, but still if we have more sort of industries coming in and setting up their labs or setting up some sort of development boards which students can just start exploring it in the right in their college along with the coursework, they can just start exploring post silicon or even pre silicon debugs. Those things would be like much easy for them when we transition to industry. So basically the KT sessions which we get in the industry at the start could be reduced. So we just get the same knowledge at the college level along with the course.
Interesting. And what's the industry perspective to this?
Yeah, I think I'll just take a step back. If you look at the history, right, academics and industry has to go hand in hand. But if you look in the past, basically, for example, if I already have 20 plus years of industry experience, and when I was at college, uh, basically during my bachelor's, I basically got introduced to what is computer architecture. And in my master's, exactly, I know how does it work, how does the CPU design and everything work. I think in the last 15 years, if I'm not wrong, it's more or less the same. Nothing has changed with respect to the academics perspective, because I think what we have is x86 and ARM. They're more closed, and it's very like industry was not open to giving that baseline to get started, or it's very tough to get started on that.
So what more should you be doing from
Yeah,
a
that's what I'm coming at now. So basically now, in the last couple of years, I see there is some change, but I still see there's a lot of gap. Frankly speaking, from the academics perspective, right? The students who get onto the bachelor's, they don't have any idea like what they want to do, at least from the Indian perspective, right? So maybe the first 2 years, if they can focus on getting the breadth of the coverage of what is semiconductor industry and every other aspect of it, in the next 2 years, maybe after the end of 2 years, right? They can have some collaboration with different industries, like whether it is front end, back end, packaging, on different aspects, and get to them a vision of what they're going to lead into it, and figure out their interest. And then if you line up their interest, and like now with RISC-V coming into the picture, frankly speaking, even without even industry getting participated, you can get stuff from the open source. For example, this is one of the things which I was trolling with my colleagues to basically give an academic project, saying that now there's a chat GPT and there's an open AI. So basically people can pick bits and pieces of code randomly everywhere. And then if they can assemble a basic RISC-V processor and do some basic arithmetic instructions, right? That itself is a big deal. So I think that is a simple step to take forward. And once we get to that stage, I think things will slowly fall in place.
Got it. Thanks. Um, so question for you, Professor Kuruvilla. Feel free to jump in, please.
Yes, so
How?
can I make a comment on
Oh,
this
absolutely. Go ahead, please.
university curriculum? So I'm not a person who tracks university curriculum, but there is one thing seriously wrong with the university curriculum, that they teach in undergraduate program a lot of kind of outdated technology, okay, which need to be, like, the professor from PES University said, they are the autonomy, that they can change the syllabus curriculum. So this should be done in Indian universities, undergraduate universities. A lot of, outdated things should be removed, and the VLSI education is very lacking. And this I can understand from that industry perspective, and that should be very seriously looked into. And definitely, I think the university UGC or they have their own problem of giving autonomy to universities, maybe evaluation, grading, and all that. But this should be done in universities, and it's not a problem for IITs or IIScs where everything kept updated. But this is a serious thing which should be looked into.
Absolutely. Yeah, I'll take a quick segue, something I remembered related to this question. Up until recently, pre-COVID, I used to go for campus interviews and just campus events a lot. And consistently going to some of these top schools. I used to go to Stanford and Berkeley, and it'd be a bunch of these hardware companies with their booths. with 2, 3 students, and there'll be a huge line in front of, the Ubers and the DocuSigns, and I mean, all of these companies for students going into software. And it's always been, and now we see a tremendous improvement in how hardware is coming up, right? Open architectures, and but I'd like to get the academic view on this. How do you see students, inclined towards hardware versus software? And we've got
Yeah, that's a good question. Yeah, the students will be inclined based on where the jobs are. That's the end thing, right? So, as the with the growth in the jobs in the hardware sector, you'd actually find more students going towards hardware-based interests and things like that. But on the other hand, my personal experience is the students who do get their hands dirty, try out stuff with hardware. Um, it could be maybe at the the RTA level, or in fact working do something at the microcontroller or interfacing something. Their interests essentially supersedes and they are essentially able to make a decision which is different from the rest of the crew. So they could possibly that interest could actually lead them to a direction which they would then take on for a job and a career later on.
now certainly it helps if there are the right opportunities available. What do you think?
Absolutely. I mean, I completely agree with what you say, right? The challenge of hardware and software is always there. I mean, whatever looks fancy, nice software, people want to get into it, and students are also attracted in the same way. But if I request the industry to come in and pitch in at this point, if we could showcase, right, 1 or 2 or 3 use cases that you have worked on, which are hardware oriented, really difficult, and you have solved them, and the excitement that the accomplishment and all of that comes through the process, I think students are motivated. They only need direction towards, external motivation. I would say if I go tell them, this is fantastic, they will listen to me. But then the industry plays a very big role in that because ultimately, what do you want the student to end up with is having a job, external job, right? So the industry folks, you guys, if you can come in and showcase the kind of projects that are happening, and that will build excitement to get them going.
So
That's all that is needed, I think.
yeah, I'm going to pull on that thread a little bit with Sharnesh here. Any of your classmates or your friends who move to software, if all else being equal, can you think of any reasons why they would go to software versus hardware, assuming you've got opportunities in both places, right? What is hardware kind of missing from a student perspective?
Yeah. So I completely agree with what Justice has said. It is mostly like what students have experienced in their college life. They just wanted to continue in that. Don't want to jump to completely orthogonal thing in the industry when they move on. So if we have people who has experienced some hardware or some courses related to RISC-V or something in their coursework, of course I can bet on that most of them would always continue in that same industry. But since like the number of people who are getting exposed to actual industry level curriculum in the college is very less, so people just sort of try to go on a safer side to the software thing, which is being much more exposed than how hardware is being exposed. So in that case, if the number of people who are being actually trained on hardware, and if the industry can come and give sort of what sort of roles they offer and what will be the like challenges which industry is solving and how exciting it is, students will be of course interested to come and join them and solve those challenges.
Interesting. So changing.
So I
Go
just
ahead.
want to add one point, right? Especially in the students, something again that as faculty we notice that a lot essentially comes from seniors. So since the seniors have done something, therefore everyone has to do the same thing. So one way which we can actually help is at least for a period of time open up internships in hardware, so that even if you get one batch of students interested, that would create a tradition, and the rest of the students would essentially follow for like a couple of years.
Is that something that's done at an academic institution level, trying to, you know, I hate to say push, but trying to influence the students towards going into hardware?
Uh, so again, the students look for opportunities. Some of them essentially are they like they would probably take a course somewhere in their curriculum, and then they would get interested in that and want to essentially go further into that aspect. But so what really happens, and this student would be like the minority at maybe in a particular year who would possibly take a hardware route. But then if the other students, perhaps juniors, essentially see that, okay, this senior has done this, taken this particular route and has been successful, then they would also follow, right? So a lot goes from what like their seniors essentially tell them. I think the students would actually agree with this.
Yeah, so what we need is
Can
to
I
find an educational
pitch in?
institution which is just starting and then have the first batch go into hardware. Sorry, Professor, you're
So,
saying?
yeah, so I just want to talk about this hardware, software, because I am working in a department called Department of Electronic System Engineering, which has been identified as a system, hardware building department. And we have three programs, electronic system engineering, electronic product design, and microelectronics and VLSI. And what we have found is that there is the best students, join our program. And other than computer science, the computer science, of course, goes parallel. So we never faced any problem with people opting for hardware design. Even within our department, if they have a choice, they would opt for a chip design than an embedded kind of project.
Go ahead.
Yeah, I want to step aside a bit and take it a bit in a different direction. So I think it's more what are the students exposed to, and the way I would like the industry to participate here is not at the end of the when the student is about to graduate, but if the interactions are all along the career, all along the program, right? And they know that okay, these are the kind of exciting things that happen in the hardware industry. This is what I mean. I don't even want to call it hardware, right? They, I mean, awareness of what is it that I need to know all of this. It's not that, oh, let me not look at it. That's not what I'm going to do. No, I need to have the breadth. So the interaction should be all along the program. It's not, we produce something and you consume something. Students are not, I mean, the industry academia interaction should not be that way. It should be all along, right? If we have, in any form, right? If the exposure happens um, often, I'm sure there is more excitement. So something, let's say we have a talk, mm, comes in and somebody comes in and talks about, okay, then you go back to your curriculum and say, okay, yeah, this is very important because, I heard this from an industry talk or some, research talk.
Is that a norm where you have guest speakers coming in and talking about what they're doing in the industry right now?
Yeah. So we in fact do have that. If anyone in the industry wants to give a talk, they could just like contact any of the faculty, and then in many cases, like it can be done during the semester anytime. So we're very open, and I think most colleges are open to industry talks. So in fact, I think for some time there was also a course called professional something, where every week there was a talk from an industry. So such talks are actually encouraged in colleges.
Got it. Thank you. Changing topics a little bit. So when you go to recruit at colleges, right, what are the top three things you're looking for? And how can students be better prepared for it? And how do teachers be aware or professors be aware of this is what companies are looking for?
Yeah. So when we go to the colleges for recruiting, right? I think primarily we look at thinking is, and when you give certain hints to that problem, how does his style of thinking change?
Can you elaborate on that a little bit, just as an example?
Uh, for example, like a general example, right? Uh, let's uh, uh, let's take a simple example. We have this conference room here, right? Now, basically, like I have multiple doors here. I want people there are 300 people coming in, and we want this entire room to be fitted in less than a couple of minutes. So, what is the process, or how does he manage the people to get in and get out? with the least interference, right? Some people might come up with a approach of saying like, hey, I'll give a numbering scheme of 1 to 10. People can come in, then 10 to 20, then how do you organize and everything, right? So they might, this is one of my very common questions for all the engineers I ask.
So it's really problem solving you're looking
Yes,
for, right?
that's what. Like I say, I have 20-floor building. I have 4,000 engineers which need to get into the building. Everybody comes at 9 o'clock. So, and within 15 minutes, everybody should be done. And there are 8 elevators. Each can accommodate 50 engineers. How do you do that?
Got it. Got it. Can you change that a little bit and talk more about from a compute or RISC-V, right? If you go, so let's say students are great at problem solving and the motivation levels, right? What's the next level? What are you looking for? What are the basic skills you're looking for?
So, for example, if I am looking for on the compute skills, right? The things which I look at it is, can they know about the basic pipeline? Okay. Once they know about the basic pipeline, let's talk about front-end execution. What is the basic things which happen, whether it's branch prediction or not? Something on the people may not go into depth of it, but at least on the high level, they should know the details of it, so that they can have the complete visualization of it.
Yeah, this is great because right there are like 3 projects, right? You could set them up as projects and provide to colleges, right? So changing tracks a little bit and talk more about open source. Um, where do you think, and maybe Professor Kurvala, if we can start with you, is what kind of, how are we incentivizing students to go look at open source right now? Or if you're not doing it, and whether you think we should be doing it?
Yeah, I think we should be doing it because I must say that we started this RISC-V design way back in 2015. That was for a MIT project. And we started with the MIPS, okay? At that time, a colleague of mine, Professor Bharadaj, suggested me that RISC-V is coming up, and we looked at it. And the first of all, RISC-V was well defined and amenable to hardware, and these lot of licensing and NDAs and MOUs, all that can be avoided, and a lot of things are available, and in academic it enhances learning. It enhances learning and research and all that. And so I think this open source, um, I mean, it need not be sold anymore. People know about the advantages, and the hardware was lacking in that way. So I think we need even in the VLSI domain a lot of open source tools, which is lacking now. And I'm sure this will enhance the system building, education, and research.
Yeah, I will say this from a I guess industry perspective. I'll put that hat on. Is if we see a resume where somebody has a link to their GitHub, that bubbles to the top. That to us tells us that that particular candidate has explored beyond what's happening on a day-to-day basis. So, but continuing the same question, right? From an open source standpoint, where do you stand, and whether the academia is doing enough?
Yeah, so IIT Madras, especially, I think we've started working with RISC-V, I think, before I had even joined. We have the Shakti family of processors in Madras, which started mostly from students, built on the RISC-V and so on, and essentially now is being used in seeing multiple applications and so on, right? So one thing which has actually been great with the open source hardware in particular is that now you can actually study computer architecture without actually relying on just simulators, right? So prior to RISC-V and prior to this entire open source hardware, if you want to actually do something on something in computer architecture, you'd have to rely on simulators like Gem5 or things like that. And now you can actually realize it on hardware. You can actually put it on an FPGA. You can actually see it functioning. And so this actually interests a lot more students, right? Like as I did mention, it lets them see something in practice, gets their hands dirty, and then it influences them for life.
Could you add
So
something?
I'm also all about open source, right? Completely agree. I say that all the time. It's good to have a GitHub saying that, I did this chip with open source tools. Do it yourself, and not that, I did a course that taught me this. Instead of that, you should be able to say, I designed this chip. And all of it is possible now with open source. We go through, I mean, not going into the details, but we go through the entire design flow in the course that we teach at undergraduate levels. So I motivate them to say that, okay, take a RISC-V, put it and say that, I have done it. And I think the students are, I mean, give you numbers, I think about 95% of the students in my class had this entire chip flow done, right? So students do
That's
it.
really impressive.
Yeah. They do it. They just need to be given pointers saying, this is where you need to look for to do it. I think if we can, put it in place in such a way that students have direction, and I emphasize this all the time, right? University is the playground for exploring projects, and you can fail, it's still good, you learn a lot. That's the place where you can explore, do all kinds of exploratory work which may not even be done in the industry because of other legacy issues and, other tools. Here, if you can play around, come up with something which is, very quick, very easy, even if you fail, you have many things to learn from it, right? So
And you
open
don't have,
source is the best place.
yeah, and I do not have to deal with tools, commercial tools, and the
Absolutely.
MOUs and the licenses and all the logistics that comes
Absolutely.
with it, right? Yeah. And then at least from a company standpoint, we do a lot of open source at our end. But I think Bob's about to kick us out of the door. So thank you so much for a very lively discussion.
Stay. I just wanted to thank our panelists, especially the professors, and we're going to owe you one, but we have gifts for you. Thank you so much. All you do for the students is very appreciated. So thank you so much, and thank you so much for being here and being a part of this.
Thank you, Professor.
Thank you.
Thank you. So is our next speaker ready to come up? So it's kind of fitting that our last presenter today, before Jim gives the closing words, is the person I probably had the longest, deepest technical conversation with yesterday. So, Gautham, it is your privilege here to bring us home.
Thank you so much.
You bet.
Bob, how do can I get something to
Oh yeah,
slide there?
it's up here.
Okay. Okay, so good afternoon, everyone. I hope I'm clear. Quick introduction from my side. So I'm Gautham Kripalani. I work at Codisip. I'll tell you a little bit about them in a second. I basically head up their technical sales and field application engineering groups. So let's dive straight into it. So if you look at Codisip, it was a company founded in 2014, right? They're based out in Europe. So all of the R&D is in Europe. So everything in purple is in Europe. And those are the R&D centers. That works quite well for us in today's time with all of the geopolitical situation going on. It's about 200 employees, but we're growing quite quickly. So we plan to actually expand that to 300 this year. What we actually do, I want to kind of build up to it, but fundamentally speaking, we do RISC-V CPUs, but we have a twist to it. We enable fast customization to really tailor your hardware for the solution or the target market you're going after. So we are one of the RISC-V co-founders in 2014, one of the first providers of RISC-V core as well. And as I mentioned, the key kind of takeaway of here is custom compute. Before we go into the actual solution, let's look at what's happening in the market, right? So if you go back to the 1980s, you had companies like IBM, which were completely vertically integrated. So they did their own processors, they taped them out, they did the boards, they did the total solution, end to end, right? Then the market changed. In early 2000s, you had companies which were doing domain-specific stuff. So you had people like Synopsys who were doing IPs, but also EDA tools. You had companies like ARM, Imagination, doing just the IPs, so processor IPs. You had the fab guys like TSMC doing their own fabrication. So you kind of got it disintegrated over here, right? Everyone was doing their own niche little thing. That did add some significant value. But if you look at the trends today, it's actually shifted back. And the big OEMs that are really doing well are the ones that are doing now, again, partial vertical integration. So if you use Apple as an example, quite popular, I think most of you know, they design their own chips, right? So the model of buying off-the-shelf chip that is used with your competition doesn't give you that USP in the market today. So if you want to actually solve that solution, you've got to go back to the bases. People like Apple, Tesla is another very good example in the automotive space. So they are actually going and designing their own chips. They have some of their own in-house processors. Some of them they obviously license. They're not obviously doing the fabrication part, they're fabless. But the whole point is the OEM is in principle the end user right at the top of the stack. And they're going back to the bottom of the stack to really dictate and build hardware that meets their software requirements, their target applications for their target market. So now if you just look at the market cap, right? So market cap, it's a little bit more of a business slide, but it actually shows you, right? So someone like Apple, which was in the same market as Nokia, their market cap is significantly higher. The same thing with Tesla, right? So obviously, I'm not saying that that's the only reason why their market cap is so big, but the fact that they can differentiate at the semiconductor level is what actually differentiates them in their market space compared to the traditional automotive players that we have out there. So vertical integration driven by the OEMs where they are customizing, building, designing for their use cases is really where we see the value in. Again, if you look at the financial side, I'm not going to spend too much time here. Massive potential of growth, right, if you can actually dictate and drive this. But let's actually look at the technical side. There is a problem brewing in the background. So all of the fundamental semiconductor laws are starting to fail, right? So if you look at Moore's law, Dennard scaling, all of these are starting to fail. What you used to get 10 years back when you went from one process node to a lower process node and you were doubling up on PPA, which is performance power area, is not really happening anymore, right? You can see that quite now with the lower process nodes in the sub 10 nanometer space. Further, if you look at the economics of it, previously to do a high-end ASIC tape out would cost probably tens of millions. A fab was 1 or 2 billion. Today, a fab is 20 plus billion. A high-end ASIC tape out end-to-end is a couple of 100 million, right? So we're paying a lot for it, but you're getting diminishing returns as we move forward. So how can we actually solve this, right? Especially in a time today where semiconductors is in the limelight, there's chip shortages, people want better performance, lower power, obviously smaller area for cost reasons. Thermal is becoming an issue as well in certain markets. So how can we actually solve this issue? There are a couple of different solutions out there. We are lucky to work in a space where there's a lot of innovation happening. There's lots of cool technology out there. So one option could be, okay, move away from electrons, switch to protons. So this is more for the physics people in the room. Very interesting. It's been going on for quite some time. But is it really in a state of mass production? There are companies, startups doing research in this space. Me personally, I think it's going to take another 10, 20 years before this becomes anywhere close to mainstream, right? If we then look at silicon, right? So there are other solutions out there. Nanotubes is something which is quite popular. It's quite the buzzword. But you have the same issue here. It's not a short-term solution. It's not something that's going to happen in under 10 years, right? So what you're really left with is customize the hardware. The concept of having general purpose hardware and then you go and try to tailor your software for it doesn't really give you the best of the best. If you want the best of the best, customizing the hardware is where you end up at. So, this slide's kind of trying to summarize this point again. So of the solutions out there for short-term gain, and again, looking at the market trends and what these companies have achieved, customizing the hardware for your workload. So whether you call it acceleration, domain specific, whether you want to look at it as a heterogeneous compute, it's really, in my point of view, very simplified. You tailor your hardware, design it in a way that it meets your specific application requirements for your target market. That's the kind of key point. So keeping that in mind, okay. I'm losing control of my slides. Give me a second. Okay, I seem to have lost an arrow here, but fundamentally speaking, when you look at customization, there are different phases of customization. What most people do is you can customize your software. So you buy a ready product, so a board with a chip on it. You try to customize your software to extract the most value from it. The next step or the next level down is customize your hardware. So again, you're having a standard chip from a standard chip C itself. So this is when you can actually take different standard building blocks or standard IPs or standard processors and try to do things at the SoC or the system level to optimize PPA bandwidth to get more kind of performance for your use case. But why do all of that when you can actually go and customize the processor itself, right? That's right at the bottom. If you can make changes, customize it, tailor it at the processor level within an SoC, that's why you can extract most value. So what are the benefits of custom compute? You can improve performance, right? There's two ways of looking at it. Sorry, I'm losing my slides again. One is cost-driven. So if you want to use older process nodes but still get a better PPA, customization will help you there. Or you say, I'm going to use the latest and greatest process node, but I'm going to extract the most value by, again, making it tailored for my use cases, right? The other one is improve efficiency. As I said, in some markets, power is really critical. Thermal is becoming a problem in automotive. Cost, again, reducing area is another aspect as well. So improving efficiency is another key one. But for me personally, the last one is quite critical. It's differentiation, right? If you want to have a product that's unique in the market, it's not another Me Too solution. If you want to beat the competition, if you customize with your secret sauce, the processor itself, that's what gives you the differentiation in the market. So why RISC-V, right? So why did we start off with RISC-V? So everyone's been talking about open standard, right? So it's an open ISA. Unlike the other providers in the market, RISC-V doesn't limit you. You are allowed to customize the ISA, the cores itself. So that's one of the reasons why RISC-V is really kicking off, and it's a great solution in terms of custom compute. It's a modular instruction set architecture. It does have a base core, which you have to comply to, and then it has the concept of extension. So a simple example is you can add a vector extension to accelerate those kind of functions. But it also gives you the openness to have non-standard extensions customize the instruction set itself, right? So that's wherein you can extract the most benefit. So if we jump to the next slide, this kind of explains it, right? So this is a simple plot of performance versus area and power. You've got the base code down there, and then you can start adding the RISC-V extensions to get acceleration for certain types of functionality. But what if you didn't want to go all the way up there because it comes at an area cost, right, to get some level of performance boost? And you can actually add in tailored customization, a subset of instructions, for example, change the microarchitecture, wherein for a small area growth, you actually get a significant boost in performance, right? And that's kind of where we are leaning toward, get the best of all worlds. So we have done a couple of simple implementations, and we just want to explain the concept here. So in this example of here, we've just done a pattern recognition example, wherein we have gone and customized a simple 3-stage, in-order embedded core. And what we are seeing over here is, obviously, there is an area growth. So it goes up by about 50%, but the performance gain that you get is 5x, right? So a significant boost in performance for a small area growth and correspondingly power as well, right? The concept is, what we're trying to show is that you can, when you start tailoring for your use case or your market, in this example, it's AI or pattern recognition specifically, you can actually get significant gains in terms of performance or acceleration with, small trade-offs in area and power. If we then just look at another segment, so this is the wireless or the 5G segment. Again, we've just done a bunch of simple examples. So if I just look at the FIR filtering accelerator, so over here, we are getting 40% inter where we are doing the sorting in a parallelized form as well. And the first example is really a butterfly operation for an FFT accelerator, wherein again, we have implemented this ALU logic unit, which is accelerating those kind of functions, arithmetic functions, right? So again, the key point we're trying to make over here is that these are simple examples that our solutions teams have implemented, but it goes to show that when you customize and when you know your end use case in mind, you can actually get significant gains by tailoring your hardware. So this is one of the lines my CEO loves to use quite a bit. So it's all about evolving and adapting, right? So the ones that survive adapts to the environments that they are in. It's not the strongest, it's not the smartest. It's really the people that, or the companies or the organizations that can adapt to the changing environment, right? We have a technical problem. Scaling is failing. We need to get better PPA. Customization or customizing for compute is one of the ways forward, and RISC-V is that vehicle which actually lets you achieve that. And just on the final slide, so what is Codicip doing to actually help you achieve this in a timely manner, right? So it's all well and good to say, yes, you can customize your hardware, you can customize your software, but it comes with its complexities, it comes with its challenges, right? You're talking about going and changing RTL code, Verilog, changing compiler code, all of those aspects. So what we provide is we have the standard RISC-V cores. You've got your embedded application cores, tape out quality. You can just take them forward like with any other business model, put it in your SoC and tape it out. But if you want to start customizing, what we have is a tool. It's a one-stop shop. So you can come in, you can profile your applications, right? You can see what the hotspots are. You can start customizing within this environment. So we use a high-level abstraction language here called Codal. You make modifications there. It auto-generates the compiler, so you don't have to touch the compiler. The compiler can pick up the new instructions. It auto-generates the RTL as well, so you don't need to go start playing around with Verilog and changing things there. It gives you a verification environment. This is all your secret sauce, so you don't have to feed this back into our organization. So you can go build that unique selling point for yourself, which will belong totally to you. And you don't have to do this by hand, right? So it's all about fast time to market. So that's the solution that we're looking to provide here. And it's actually had a massive adoption. And it solves the problem, right? Because people do want to customize. It's just that the fear of customizing something as complex as a CPU always sticks around. And helping that process and giving faster time to market is what we solve in this space. I think with this, I'll... Hey. Thank you. Thanks, Bob.
Hey,
Yeah.
Can I steal that?
Yeah, no worries.
Hey, thanks so much for being up here, Gautham. You arrived just in time for the presentation. So, do you have any questions for Gautham before he gets off stage? Oh, we have a question. Gautham, here, you take this. Jim.
Yeah.
Okay, thanks. So, yeah, I completely agree with you. The trend that you see in terms of requirement for the custom compute and the reasons that you mentioned about how do you differentiate basically when you have saturated on certain aspects, right? One other aspect to look at it is, the standard products they sell in volume, basically, right? Whereas there will be limitation on volume when you go custom. Are the OEMs or customers willing to pay more for the custom products for the differentiation that it brings? Is that what you see?
Definitely. In some of the space, we are seeing this trend because by customizing it, it makes them unique. So they are willing to pay the price. Obviously, it's driven by volume. So the customers which have high volume don't mind going through the effort of customization because they have that volume to justify it. But definitely because of the differentiation that it brings around for them in the market space and the control that it gives them. So like if you take automotive as an example, without quoting any specific names, like the OEMs definitely want control. They believe that generic solutions out there are not meeting their requirements, right? So they want to have that control, but it's a new thing for them, right? Because they are sitting right here, they've got the tier ones, the tier twos, the semicon guys, and then the IP guys sitting in this space, right? But they're definitely very keen on this. And then if you look at other consumer markets with high volume, absolutely.
Okay, last question here.
How resilient are your customized solutions as such? In case if they fail,
Sorry, can you repeat that again?
how resilient are your customized systems as such? In case if they fail, how you are going to?
Okay, so that's an interesting question. So we provide soft IP. So we are not providing an actual chip. It's just a processor, soft IP with this tool, right? The whole business model or the idea is that the customer customizes for their use case. They don't have to feed that back into us because that's their secret sauce, right? And they want to own that. So the verification part is wherein we assist, we give an environment for it, but it depends on them to complete the verification. Obviously, as an organization, doing IP, we are absolutely here to support our customers, and in some cases, actually even, take on some of the workload. But the end goal of customization is they do the changes, they own it, they don't have to share it back, but then the verification part of it also lies with them. Yeah.
Thanks, Gautham.
Thank you.
Take care.
All right, so is this on? Hello, is this on? Yeah, that's better. Yeah, great. Hey, first, thanks everybody for coming out. We had this idea, like, I wanted to meet more people doing RISC-V, and I thought, well, I'll just throw a conference and do it. And also, I really like, there's a couple of RISC-V conferences going on, and some are officially promoted by the RISC-V, is it international? Yeah, RISC-V International, they do a great job bringing people together. But I was literally joking when I said I just want to have nerds talking to nerds, and then they named the conference that, which is pretty funny. And then I found out lots of people self-identify as nerds, so that's great. So again, thanks for everybody showing up and talking. I always find these things, it's partly about like listening to the talks where people prepare, and it's partly just hanging out and talking in the hallways. And I talked to a lot of people in the last couple of days. I especially appreciate the students that showed up. It's an interesting, daunting world because some things are so much better. RISC-V is really cool because you can do computer architecture projects, you can try things, you can play with it. The open source hardware stuff is really cool. But they also said, some of it's really hard. There's gaps, there's the stuff that's broken. I really like the comment about one thing really cool about FPGAs is you can now go from concept to simulation to put it in a chip and run it. So I'm going to send a note to some of the students and professors we talked to about like what's good and bad and what's missing. I was talking to Divyang about one kid. Everybody looks like a kid to me, by the way. One kid, he's probably 25 years old and really smart, and he said, what did he say? No, I'm drawing a blank. He said, oh, we can do a lot of CPU stuff, but we're missing tools to do validation on SoC components and I/O and other things. And we're actually building some of those components. And we need to go talk to people about how do we upstream and open source some of those pieces. But I kind of feel like you look at everything available and there's so much available, it's hard to see what's missing sometimes. So I think next time we're going to we do this kind of thing, I'm going to really ask people to come in and talk about what they need as opposed to what they're doing, and then go try to fill in some gaps. So I think that would be really interesting. And then the other thing, I came here and I wanted to announce, I want to have a contest. And what I really want is, a contest of who can generate the best RISC-V processor using AI. And I feel like we're not quite ready. I talked to a lot of students again, and they said, it's good at some stuff, but there's a whole bunch of gaps and things. So we're going to we're going to solicit some input on what steps do we have to take to make that a reality? Because I think it'll be really interesting. We've talked about internally, we're using AI to write code, to assist on code, to do validation, to generate test benches. But to actually generate computer architecture and models and everything, I think it's going to be really amazing and transformative. But I think we need to get to the point of like how do we create the right tools so people can do this really in an interesting way. So anybody has an opinion, you have our emails, send it to us. And I'd like to do a couple of maybe we just do live stream events where we get and talk about it. There's some really cool events where people are doing stuff on open source hardware. And we're going to start to participate in that and figure out how to help out. So just listen, watch for that. We'll be talking about it as we go. Sorry, I've had a really long week. I'm drawing a blank on the next. What's that? Yeah, it's been a super adventurous time. And finally, I'm just amazed at how much energy is in doing design. And I really want to thank Naveed, who said, It wasn't the business model, it wasn't the performance, because people ask us, is it 2% faster? No, it's the innovation rate and the ownership and the change. And I see that all the way down to like the student level, which is really cool. So I just want to say thanks again, everybody, for coming. We're going to do another event like this, you know, the same kind of level. I think we're going to talk to a lot of people about what they liked and didn't like, and really appreciate the feedback. But thanks for participating, and we'll see you again soon.
So folks, we're done. Go enjoy your day. Have a great weekend. Take care. Oh, and by the way, eat before you go. Bye.